I'm a PhD student also from the National Center for Nuclear Research in Poland, and I will tell you about searching for AGNs in small data in this case. So first let's talk about the AKARI data. It was an infrared space-based telescope launched by the Japanese Space Agency in 2006. It performed the all-sky survey in mid and far infrared and 2 deep surveys in near and mid-infrareds. And in the case of the deep surveys, you see that the passbands used by the AKARI satellite were quite narrow. So we have 4 different filters, 2 of them in mid-infrared, one centered in 9 micrometers and the second one at 18, where white filters covered the area of the other neighboring filters. So we were working on the AKARI NEP Deep survey, which obtained around the North Ecliptic Pole. It obtained the source catalog of around 23,000 objects, and 1/3 of them had optical counterpart. And also there was another survey, a deep survey performed by AKARI NEP, AKARI satellite, the White survey, also around the NEP region. And because we were using the supervised learning algorithm, we had to make a labeled data set, and in the case of the NEP Deep survey, a really small number of objects had the spectroscopically confirmed class. So because of that, we used the data from the NEP White survey as a training set where such a dedicated spectroscopical surveys were performed. However, we need to remember that this survey covers wider area, but it is a shallower one. So we used the support vector machine algorithm here. The main idea is just to map the data into the higher dimensional feature space where the separation becomes possible. And mainly we use the modified version of it, so-called fuzzy SVM, developed by Lin and Wang in 2002. And in this modification, we connect each training object with this so-called fuzzy membership, which describes its importance in the process of creation of the separating hyperplane. And we construct the fuzzy membership on the base of the measurement uncertainties. And because of that, our SVM algorithm just used the objects which were measured the most precisely to construct the separating hyperplane. And because of that, it was more physically motivated classification. Our data set was quite unbalanced, so we used the proper evaluation metrics with the Cohen's kappa and Matthews correlation coefficient, which shows the agreement between 2 raters, so the true labels and the output of the classifier. Also, we use the precision and recall, which can be interpreted as a purity and completeness of the output AGN catalog. And the main evaluation metric was the area under the receiver operating characteristic curve, which was maximized in both the shallow and the deep grid search process. So main properties of our classifier were that it was a fuzzy SVM binary classifier, AGN versus the galaxies and stars from the AKARI NEP Deep data. Training data was mainly constructed from the AKARI NEP White survey. The kernel functions used by SVM were the sigmoidal function and the radial basis function. Area under ROC curve was the main metric maximized in the grid search, and we used 5-fold cross-validation. Okay, so in the case of feature selection, we need to remember that we have the strongly decreasing statistics in the case when we are moving to the longer wavelength. So here you see the objects that have measurement in a 2 micrometer passband, and then when we go to the longer wavelength, the number of objects strongly decreases. However, on the other hand, this mid-infrared passbands, they are the most important in the case of the selection of AGNs in the infrared. So on one hand, we have bigger statistics but smaller amount of information about the objects that we want to search, or we have the smaller statistics and the bigger information about the particular objects. And also the really small was the amount of training data, but because even when we took the data from the AKARI NEP White survey, we still have only such amount of training objects. So the really proper, accurate performance validation is really hard in this case, and also we need to remember about it when we are using the feature selection techniques here. So our feature selection technique strategies were such that first we were trying to separate objects which had measurements in the near infrared, so we tried to preserve this as big number of objects as possible, so we create a classifier that use only near infrared passbands and only the mid-infrared passbands, fluxes and corresponding colors of neighboring filters. The next feature set was made as traditional as possible, so we just took the colors of the neighboring filters. The next one was to use also all possible passbands in near infrared and the white filters in the mid infrared. And also we used the feature selection feature selection method based on mutual information, which measures the information, the dependency of one feature to another. And we used, in this case, to select the best 10 features, we used all fluxes and all colors, and also we made a polynomial, second-degree polynomial features of all these fluxes and colors. And first we look at the performance of the radial basis function and sigmoidal kernel. Here you see the metric value and the type of metric. As you see, in all cases, in all feature sets, the RBF kernel performs better. So in the next slides, we will only consider the RBF kernel. So here you see the same results, but only for the RBF kernel. And the 6-color classical feature set and the mutual information feature set, they show the best performance. So we used, so these both are the best classifiers we found. However, we need to remember about this, the thing that previous speaker was talking about. So we have some manifold described by the training sample, but the volume described by the generalization sample, even if we are cutting values of the particular filters, is somehow different. So we need to know what is the extrapolation ability of such classifier. So we divided our labeled data into the 70% of training and 30% of validation, where we took the objects with the highest redshift or the faintest fluxes. And here you see the performance of different classifiers. Of course, the most important value is the performance of the classifier on the whole labeled data set, because we have too small amount of data to properly evaluate it on the test set. However, still it's good to know if your classifier not fails completely in the case of small extrapolation. So as you see, both the 6-color feature set and this mutual information feature set, they both perform quite well, so we will use them as a final classificators. After obtaining the final catalog of objects, we also use the Platz probability estimation, which is based on the distance of objects from the separating plane, to create a more reliable final catalog. So as you see here are quite weird probabilities, because the Platts probability in the case of unbalanced data sets, it's moved towards the bigger class, which are the galaxies and stars. However, we still can use it to choose the objects which lies as far from the decision surface. So at the end we obtained this two different catalogs of objects, and after cross-matching them we obtained 216 objects in the final AGN catalog. And well, it's our final result for now. The main idea was not to have the complete catalog, but to have the most pure possible catalog of AGNs from the deep infrared survey, and now we would be able to make an observations for them, because probably these are the covered by dust AGNs, and they are quite interesting from the astrophysical perspective of view. And when this work will be finished, it will be submitted to the Astronomical Society of Japan publications in the AKARI special issue. So thank you.